Hello, everyone. My name is Mihai Franco. I'm a postdoc at the University of Copenhagen, and I will present to you the showcase entitled Negative Jacobian Free Simulations Using Principal Stretches. Element inversion is always possible when doing finite element simulations. Even if the energy is infinitely large around zero, the solver can still encounter inverted solutions. Many energies are not even defined for such configurations. Existing solutions from computer graphics modify this energy or its gradients. But we don't want to modify the material model, and we don't want to have inversion either. Our solution is to constrain the solver to never reach such potential solutions. I'll briefly introduce the mathematical setting of first-order FEM. I will use triangle elements in 2D, and I will also show results in 2D. As you may know, deformation is measured by a special matrix F constructed from the current positions and the undeformed ones. Its determinant J tells us how the area of the triangle changes. Most textbooks assume that J is positive, as a negative value would not be physical. However, in practice, elements often invert, which means that J becomes negative. Another way of identifying inversion is through principal stretches. These are the singular values of the matrix F. For our special case, we need to make sure that the orthogonal matrices U and V are pure rotations and not reflections. This is done using a technique introduced in graphics by Irving et al. Once this is taken care of, we can identify an inverted element by having one negative singular value. Thus, we identify two ways of constraining the problem: through the determinants J or through the principal stretches S. On the first row, you can see a direct approach that hasn't worked very well in practice for us. This might be due to the solvers that do not enforce strict feasibility at every step. Other solvers may not support nonlinear inequality constraints at all. A common practice in numerical optimization is to introduce the so-called slack variables Y. See the second row. An equality constraint keeps them close to the original nonlinear constraint, while the inequality is now enforced by the simple bounds constraint. The price we pay is that the problem has to be now reformulated in terms of both the variables X and Y. We choose the bottom right solution mostly because it is easier to split the objective into the work of the external forces and the elastic energy. And this elastic energy can be fully expressed in terms of principal stretches. We can now formulate mathematically our model. We have an optimization problem with a nonlinear objective, nonlinear equality constraints, and non-negative bounds constraints. We can write down the Lagrangian for this problem and derive the KKT optimality conditions. We do not include the bounds constraint, as this will lead to a complementarity problem. We will see later that we can solve these equations using the Newton's method. You can find expressions for the gradients in the paper. The problem just stated fits very well within the framework of the alternating directions method of multipliers, or ADMM. We obtained two sequential minimization problems, one solving for elastic energy using principal stretches and the other one solving for external forces. The last step is simply a scale dual gradient descent. For the first minimization, we can use a projected gradient descent to enforce the bounds. The difficulties here are that you need to tweak the penalty factor rho, and you need to decide when convergence has been reached. We do not have a clear solution yet for the former, but for the latter we use the L1 merit function with good results. Here's now a trick we use to enforce the bounds constraints. We map real values to the positive domain. Basically, it's a change of variables using the exponential map from R to R+. We can now substitute the new variable sigma in the Newton solver or gradient descent, and the non-negative bounds are automatically satisfied. Of course, one needs to apply the chain rule to the gradients. Details can be found in the paper. Although we could replace projected gradient descent with this method, we did not always find improved convergence results. Also, the Newton solvers seem to do just fine without this extra substitution in the few examples we tested. We have not tested this method a lot, as it is still incipient work. We did all the testing in MATLAB using the following solvers. fminunc for the reference unconstrained solver. fmincon was used for enforcing directly the constraints, and fsolve in place of the Newton solver. We also implemented projected gradient descent and the ADMM outer loop. In the end, we settled on 2 experiments using a box, a compression test and a bending test. As you will shortly see, ADMM and Newton were the only methods to give realistic solutions without encountering inversion. For the compression test, the box is fixed from the left side and compressed by a large force. This is causing trouble to the reference solver. Namely, it encounters inverted elements inside the solver iterations. Our 2 proposed methods give realistic solutions without this happening. In the bending scenario, we fixed the box by the 2 ends and press it from the top. Again, our 2 methods win. We also showed the reference solution for comparison in red. But this only works because MATLAB can compute a complex logarithm for negative values. This is a lot, of course, not desired in practice. We conclude that the ADMM solution has a lot of potential and bears close similarity to the existing one of Narain et al. On the other hand, it requires a lot of SVD evaluations. The exponential map is a nice trick to get rid of the complementarity and projection, but it may not be worth it in the end, as it does not bring visible improvements to either gradient descent or the Newton solver. Actually, the Newton solver may work without it, but we cannot guarantee it. We are currently working on a C++ implementation in 3D. Finally, if this works, we think it may turn out to be a very robust way of solving the inversion problem. It is also elegant in the sense that it has a lot in common with projective dynamics in ADMM, while using only a minimal set of variables for measuring strain, namely the principal stretches. Thank you for listening, and please contact me if you have any questions.